Spark's being live cast, right? Thank you. So my name is Chad Scherrer. I'm a senior data scientist at Metis, and this talk is about my library Soss.jl, a probabilistic metaprogramming library in Julia. If I had been using my computer and had been logged in, this link would get you to a live version of the presentation that would cycle through as I'm presenting. As it is, since I'm using a different computer, I think that it will still get you to the talk, and then there's a live subscript on it, and if you remove that, you should be able to follow along. So probabilistic programming comes from Bayesian analysis, which comes from this concept of, it's really important in a lot of contexts that we be able to make rational decisions. So how do we get to rational decisions? Well, there's uncertainty all over the place, and so we can either ignore the uncertainty or we can deal with it, and we can just represent that explicitly as part of our model. So a natural way to do this is to represent things using Bayesian analysis. And historically, Bayesian analysis involves a lot of pencil and paper, doing a lot of integrals. Fortunately, it was recognized that a lot of this can be relatively mechanical and can be pushed down to the level of a compiler. So that's the whole idea with probabilistic programming. There are a few places that this is really important. It's particularly important anywhere you need to be able to really carefully manage risk, areas like medicine, finance, and insurance. And in terms of modeling, anytime you have a physical system that you would like to be able to model, hypothesis testing without very strong assumptions, or generally modeling as simulation. So here's a really simple example. This is something that you might write mathematically. You may have a mean parameter that's normal with mean 0 and standard deviation 5. Sigma is let's say a Cauchy distribution truncated to just the positive part. And then each of your observations, xj, might be normal with those mean and standard deviation parameters. So a very standard thing to do then is to use Bayes' law. This is the second of 3 explanations, presumably, that you'll hear today. So as Cameron described, the posterior distribution, and I guess I can point with my pointer, the posterior distribution of mu and sigma given x, the data, is proportional to the prior distribution of mu and sigma times the likelihood, which is just the probability of the data given those parameters. So here's an example of this. If I have my original prior distribution of mu in the blue curve, then I condition on a single data point where x is equal to -5, then I'll get the red curve. And you can see that it pulls it quite a bit over to the left, but the peak is not quite at -5 because of the bias from the original prior. Okay, so in Soss, we would write that like this. We have, as I think everyone does these days, an @model macro to represent this. So this means that x is given as an argument, and then in the body of the model, we have a few different kinds of things that we can represent. A tilde we can think of as sampling from a given distribution, or we may have, like here we have n is equal to the length of x, and think of that just as a local variable. There are a couple of combinators that I've introduced. So one of them is the IID combinator. So here, if you say IID of n, that itself is a function that takes a distribution and gives you a new distribution that's just the tensor product of that many independent copies of the distribution. I asked a lot, how does Soss compare to approaches like Turing that a lot of people are maybe more familiar with? So this is, you can think of as a spectrum of specialization in probabilistic programming. So on the left you have Stan, which is relatively constrained. The parameter space in Stan is required to be a fixed dimensionality, and the parameters are only allowed to be continuous. And in exchange for this very relatively hard constraint, they're able to focus their inference methods to perform very well on that special case. Turing is on the other extreme, so it really is universal. So there really are no constraints that I know of. I believe that's the case as far as things that you can actually represent in Turing. And Soss I think of as being in the middle. So it's not quite as constrained as Stan, but it's certainly much more constrained than Turing. And the idea is that there's this top level of distributions that has to be a fixed dimensionality. But any one of those distributions can vary in principle. Of course, some inference methods still won't allow that, right? Like if you do a no U-turn sampler, then it still has to be continuous fixed dimensionality. But in terms of representing things in Soss, they can still be discrete or continuous. Okay, so let's have a look at the high-level approach. So as in any of these systems, you start with building a model. Soss is a little bit different than a lot of the approaches you'll see in that it really focuses on model transformations and model composition. So it's really common for us to start with one model and do some transformation and end up with a different model, or to compose 2 models and end up with a 3rd model. So this is how we get to, okay, here's the thing that we actually want to be able to reason about. From that, we can generate inference code, and then finally execute that code to obtain an analytical result. Or not analytical, but a numerical result. So here's an example of just sampling from a prior distribution. So if I have this model M that I described a moment ago, I have a prior combinator, so I can ask for the prior of M, and it will then give me a new model, and you can see that not only is this observed value taken out, but Soss recognizes that the N is no longer needed, so that's also removed. From this, you can, for example, say, please give me code to generate, to sample from this distribution, and it will generate this code for you. And this is literally, you can execute this code then in Julia. Of course, you often don't want to make this a 2-step process, so you would instead say, please give me rand m prior comma 2, which is just like the kind of rand calls that you're used to from distributions.jl. Okay. There's also inline conditioning is another kind of model transformation. So in this case, we have n is a function of x, but maybe I know a specific value of n that I want to be able to assign statically. So for example, if I say m of n equals 3, this will treat n equals 3 as a value that I want to inline into the model. And this can save some cycles so that I'm not computing the length every time I go through. Okay, so you can see that, the yellow here just shows we passed in n equals 3. In the original model, that was the length, but now it's gone and it's replaced with statically n equals 3. And I can sample from this, and this will give me a sample from the prior predictive distribution, which I can't really do if I let n vary. Because in the original model, I actually had this cyclic dependency unless I know one of either n or x, right? So now that's gone away, and I can actually sample from it. Okay. We can actually even do this with expressions. So here's an expression where, say I want to have a normal approximation to a Poisson distribution. I could make this substitution, mu is equal to sigma squared. And you can see that originally we had mu and then sigma, but Soss is smart enough to recognize that we need to maintain the topological ordering of these parameters. So when we did this conditioning, it actually switched those. So we start off with sigma then, and then we compute mu following that. I have some methods for sampling particles. So similar to the RAND example, this actually leverages Monte Carlo measurements.jl. And most of Soss is built very heavily on top of lots of other packages. And I have a few of those at the end to show you the things that we have as dependencies. So here if we say, let's find particles of m equals 3, the default is that we'll use 1,000 particles. So we end up with x is particles float 64, there are 1,000 of them, and here are their values just with a mean and plus or minus some standard deviation. We get that for, in this case, the data and also all of the parameters. If I want to sample from the posterior, we have to do something a little bit more elaborate. Cameron described the no U-turn sampler, and we use the same thing here. In this case, this is building off of dynamic HMC. So if I have this model, I can say, please sample using the no U-turn sampler from M, conditional on x is equal to some random values that I compute. And of course, usually this would be actual observed data and not fake data that you sample when you're doing the no U-turn sampler. But you can see I can take the samples from this and put that into a data frame, and I get a nice representation. Of course, this can naturally be sent into similar methods as Cameron described for that Turing uses. So composability. Originally, we just had this error distribution is just static, right? It's always going to be a normal for my residuals. But I don't have to make that assumption. I can actually make that be a parameter. So here on the right, we have a model where the things we have to pass in are the data x, and then also what kind of error distribution we want. And you can see the way that's used is that given the error distribution, we find a location scale family on that error distribution from the given mean and standard deviation, and then we observe the x values from the result. Okay? And so, for example, there's this t distribution in distributions.jl, and we can use that and get a similar result to what we had before for normal. This makes it very easy to mix and match, try out different models without just starting from scratch each time. It's actually a little bit more flexible than this. We don't have to have a distribution to pass in. The thing we pass in can itself be a model. So models are first class. I hesitate a little bit to say that. They work as first class in this context. My hope is that they will work as first class in absolutely every context. If there are cases where that doesn't work, please let me know, and I will try to find ways to get everything working together. So something that I've just started exploring recently is this idea of symbolic simplification. So for a given model, we can, of course, generate code to evaluate the log density, but there are a lot of opportunities for simplification. And if I can leverage something like, in this case, sympy.jl, we can represent the log posterior density symbolically. And in this case, everything that's in yellow would, by default, be underneath the summation. Okay, so this can execute then and evaluate dramatically faster than if we just did the sort of obvious thing and increment the normal each time. So we're evaluating the whole normal distribution in that case. Of course, this symbolic representation isn't usually your end goal. So I have a function called codegen. So codegen of a given model factors through that symbolic simplification and then generates code to evaluate the appropriate expression. Finally, I want to talk a little bit about importance sampling. So here we have a model P. In this case, it's very, very simple, just so that I can illustrate the concept. But really, you would do this when maybe P is very difficult to sample from. Maybe it's some posterior distribution, or maybe it's just something that's really complex. So instead of sampling directly from P, you might have some other family Q that you can sample from more easily. So in this case, we have Q is just a bivariate normal that's parameterized by its mean and standard deviation of each of the components. So the general approach with importance sampling is first you sample some x's from this proposal distribution Q, and then you apply this weight. Well, weights can be kind of weird to work with, right? Because you might have overflow, underflow, more often underflow in a probabilistic context. So instead we'll work with the log weights. Okay, so instead of P divided by Q, we'll have log P minus log of Q. And you can see that there's a natural way that this kind of decomposes, that we have some stuff involving Q and some stuff involving P. So maybe what we could do is build code to sample from Q, subtract Q, and then add P. And that's exactly what we can do. So we can look at the sample particle importance that uses this particles approach I mentioned earlier. And the blue box in this code corresponds to both sampling from the Q distribution and subtracting out its log density. And then the kind of pink, sort of salmon-colored code just adds back in the P component. And this is the result that we get. You can see that this, although it came from this independent bivariate normal, we have the quadratic shape that we would expect. And finally, if you've done any work with variational inference, you might recognize this log P minus log Q. This is exactly what we need. And actually, there are close connections with variational inference and importance sampling. So there are several things in the works. So I'd like to implement constant space streaming models like particle filter, Kalman filter, some reparameterizations like non-centering, deep learning with flux. I'd like to have a simulation constructor, and that naturally then will, I think, lead to interoperability with Turing.jl. So thank you. Also, I'd like to really, this work leans very heavily on lots of other packages, and these are the ones that I use most often. So I'd like to thank the authors of those packages specifically. Thank you.
Hello.
Hi.
So I'm actually really interested in the symbolic kind of manipulations that you do. Is there like, do you have like a rule of thumb for when it's like, this is an always evaluate like evaluate the symbolic version and kind of simplify, versus like maybe you should only do it in certain cases? Like, do you have like a good opinion about when it's beneficial to do that?
So I'm not doing anything too elaborate right now. Basically, here, let me show you in that code. Not the code, the representation. So in the yellow box, really all that I do right now is I say, okay, give me the symbolic representation, and then that usually is in a collection of terms. So I look at those terms, and any term that doesn't involve the summation index gets pulled outside the sum. And then finally, you have a collection of terms where each of them actually involves the index. But in this case, like we have the 1 over 2 sigma squared that doesn't. So then you have to do something kind of related for factors. I'm sure that there are a lot more clever things that you could do, but that's all that I'm doing at the moment.
And I assume that like that code gen is actually fairly quick, right? It's just symbolic manipulation.
Code gen is pretty quick, yeah, because it's not that big.
Okay.
And I didn't very carefully benchmark it, but in my early test, it was about 100 times speed up.
Okay. That's really cool. Good talk.
Thank you.
Also on the symbolic simplification.
Yeah.
You use SymPy. Is this just for the data structures or also for SymPy algorithms? And in particular, anything more advanced than just combining terms and factoring type stuff?
You know, the more time I've spent on it, the more it seems like a relatively simple thing. And actually, I've had some conversations over the last couple of days with Harrison Groden involving doing this directly from the Julia ecosystem. And that's something that I would love to move forward.
So are you the only person working on this right now?
Yes.
Wow, that's impressive.
Thank you.
So I have a suggestion. I'm an economist by training, and markets are great. Firms compete, and the fittest survive, and the few left. We have to have laws to stop them colluding, because colluding's great for those few. And we also, the other problem with markets is when you have a public domain, you get the tragedy of the commons, and that can be a real tragedy if somebody drives a truck through it. So my suggestion would be you guys should get together and collude, because that's not illegal in this domain. And it would be a great thing. I think I see a lot of human capital here that's really smart and innovative, and I think you could do great things together. You're already doing great things, but I mean, I've tried Stan, I've tried Mamba, I've used Turing quite a bit lately. I haven't tried this yet. It looks really cool. There was Clara. I don't know if that's disappeared or what. I haven't heard about it in a while, but I mean, that's what happens. You get all these packages, and
Right.
Which one do you invest in? Because which has the biggest truck number and it does what you want, right? Which one's going to survive? So if you get together, your truck number goes up from 1, and you survive, and everybody survives and does better.
Right. Yeah, collaboration is something that I'm very keen on. And yeah, that was a lot of what I was excited about coming to JuliaCon for, was connecting with more people and looking for those kinds of opportunities. All right, thank you.